Welcome to the deep dive. Today we're tackling something pretty specific, really getting into the weeds of a technical paper. Blackbox model provenance via palimpsestic membership inference. Our goal here is to basically give you, our expert listeners, a solid, streamlined overview. We want to unpack the key methods, the formal setup, and importantly, the experimental results about model lineage and accountability for LLMs.
Exactly. In this paper, it really frames the problem as an independence test,
Yeah.
which is critical, right? Especially now with all these huge open weight models being released and then adapted commercially or sometimes maybe unethically. The scenario they set up is pretty common now. You got Alice who trains some big model, say like a Pythia or an OLMo, then Bob comes along and uses something derived from it. Could be a fine-tuned model, could just be text generated from some Blackbox API he's running. The big question is, can Alice actually prove statistically that Bob's work came from her specific training run?
And the need for that proof, well, it's really escalating, isn't it? We're not just talking minor issues. This could be about enforcing terms of service, like Meta's license for Llama 3 needing acknowledgement. Or it could be more serious, like digital forensics, trying to trace the origin of, say, a bot network spreading disinformation or figuring out which model was used in some malicious operation. It's about building a real statistical foundation for accountability online.
And the really fascinating part, the core mechanism they leverage, is this idea they call palimpsestic memorization.
Right, the palimpsest analogy. Maybe unpack that a bit first.
Sure. So historically, a palimpsest is like a parchment or vellum that's been written on, then scraped clean or partially erased, and then written on again. But the thing is, faint traces of the original writing often remain visible underneath the new stuff.
Okay, I see the connection. So LLMs memorize data, we know that. But this paper argues it's not uniform memorization.
Exactly. That's the critical insight. The effect, the memorization strength, seems to be stronger for examples the model saw later in its training sequence. It's like the later examples partially overwrite or obscure the influence of the earlier ones, but not completely. And it's this specific non-uniform retention tied directly to the order the data was presented during training that creates a detectable signal, a kind of statistical fingerprint of that specific training run.
So if Bob's model is derived from Alice's run, even if he fine-tunes it or modifies it, that original training order signature should, in theory, still be there, faintly perhaps, but statistically measurable.
That's the hypothesis. And this leads directly to the properties, the desiderata that a good provenance test needs. They lay out three key ones. First, obviously, it has to be effective, high statistical power. You need strong evidence, not just a hint. Second, transparent. Alice shouldn't need any secret information from Bob. No asking for his model weights or his specific fine-tuning data or anything like that. It has to work based only on what Alice knows, her data, and what Bob makes public.
Yeah.
His model's output or generated text.
And the third one, which seems like the big practical challenge, is non-invasive.
Right. This is crucial. Alice can't be required to change her original training process. She can't embed watermarks beforehand or slip in special canary examples into her data set. The test has to work on the model as it was originally trained, exploiting this inherent memory property.
So no altering the past. You're testing the natural statistical artifacts left by the standard training process itself. That's pretty neat. Okay, let's dive into the formal setup then, because the statistical guarantees really hang on getting this right. They define Alice's process yielding a transcript, alpha.
Yeah, alpha is basically a sequence of pairs. Alpha chi e t I1 here, $6 is the actual training example, like a chunk of text. And T is its index in the training sequence, just its order, from 1 up to 1, where could be billions. And Bob's artifact, the thing being tested, is beta $. That could be his model itself, which they denote med.o, or it could just be some text beta $, that his model generated.
And the core statistical question is framed as a hypothesis test.
Exactly. The null hypothesis, $, is simply that alpha and beta dollars are statistically independent. So, $, alpha perp. Basically, Bob's artifact has nothing to do with Alice's specific ordered training run.
But testing that independence directly seems incredibly hard. How do they make it tractable? They rely heavily on an assumption, right? Assumption A1.
Yes, assumption A1 is absolutely fundamental. It states that Alice's training data, within the phase being considered, was randomly shuffled.
Which, for big foundation models, is generally true, isn't it? It's standard practice in most training pipelines using things like PyTorch or JX data loaders to shuffle the data thoroughly for each epoch, or at least shuffle the order of files or chunks being processed.
Correct. It's needed for good model training anyway. Helps prevent the model from overfitting to some spurious order in the raw data source. So A1 is usually a pretty safe assumption for large-scale pre-training.
And why is that shuffling assumption so critical mathematically for the test?
Because if A1 holds, and if the null hypothesis $8 is true, meaning Bob's artifact is independent, then the specific training order that Alice observed is statistically exchangeable with respect to Bob's artifact data. In simple terms, if Bob didn't use Alice's run, then any random permutation of Alice's training order should look statistically identical from Bob's artifact's perspective. The specific order $1, $2, $3, $1 has no special significance relative to Bob's model or text if they are independent.
Ah, okay, so the randomness in Alice's original shuffling gives you a baseline for comparison. But what if that assumption, A1, is slightly violated? Say there's some subtle non-randomness in how data gets loaded in a really complex proprietary pipeline. Does the whole thing fall apart?
That's a fair question. And technically, yes. If A1 is significantly violated, the rigorous proof behind the type I error control theorem 1 doesn't strictly hold anymore. If there's some hidden structure to the order, the permutations generated by the test might not be truly exchangeable under the null. This could potentially lead to inflated false positives. The test might find a correlation that's actually due to the non-randomness in Alice's process, not due to Bob using her run. However, the authors kind of rely on the fact that for major, well-documented training runs, the shuffling procedures are generally quite robust. The subtle deviations might be minor noise compared to the signal they're looking for.
Okay, assuming A1 holds, how does algorithm 1 use this exchangeability to get p-values? It sounds like permutation testing.
It is exactly permutation testing, sometimes called randomization inference. It's a really elegant idea. You take your observed test statistic, let's call it alpha, beta, which measures some kind of correlation or relationship between Alice's ordered data alpha and Bob's artifact of beta day. Then you generate, say, coordinal alternative, permuted transcripts alpha beta. You do this simply by randomly shuffling the original training order indices. You calculate the test statistic for each of these fake transcripts. Now, if the null hypothesis metadata is true, independence, then your observed statistic alpha beta should just look like one random draw from the distribution formed by all the permuted statistics. It shouldn't stand out.
So the p-value is just the rank, like what fraction of the permuted statistics are as extreme or more extreme than the observed one.
Precisely. They compute based on this rank, with some care for handling ties randomly. And this leads to Theorem 1.
Which gives the guarantee.
Yeah. Theorem 1 basically says that regardless of the underlying data distributions or the specific test statistic area you choose, as long as A1 holds and the null $8 is true, the calculated p-value will be uniformly distributed over the possible discrete values, 2 meters all.
And that uniformity is key because it means if you set your significance threshold at, say, epsilon HL 0.011, the probability of getting a p-value less than or equal to 0.01 purely by chance, a false positive, is exactly 0.01. You have precise control over type I error.
Exactly. It's a non-asymptotic guarantee, which is really strong. No need for assumptions about normality or large sample sizes in the traditional sense.
But okay, generating $100,000 permutations and recalculating a complex statistic each time, especially if alpha has $1 billion of examples, that sounds computationally brutal.
It absolutely is, and they acknowledge that. So in practice, you need ways to manage this. One way is to randomly subsample Alice's full transcript alpha. As long as the subsampling is random, assumption A1 still holds for the subset, and the permutation test is still valid, just maybe less powerful.
And the other way is to find test statistics where you don't need to run the permutations.
Right. If you can find a test statistic non-failure whose null distribution is known theoretically, or can be well approximated under the assumption of exchangeability, then you can potentially calculate the p-value directly using a closed form expression. This bypasses the need for explicit permutation simulations. And that's exactly what they leverage in the query setting.
Okay, that makes sense. It's a trade-off. The full permutation test gives the strongest guarantee but is slow. Subsampling is faster but might lose power. Using approximations is fastest but relies on the approximation being accurate. All right, let's move to that query setting then. This is where Alice actually gets to interact with Bob's model, mu batota. She can feed it examples from her training set, $6, and get back. What exactly? Log likelihoods.
Yeah, typically log likelihoods. So for a given example, $6 from her transcript, she queries Bob's model and gets log mutars. The core idea here is to see if these log likelihoods correlate with the original training order, T. Remember the palimpsest idea. Examples seen later, T is large, are expected to be more memorable or have a stronger influence on the final model state. So if Bob's model mobitar is derived from Alice's run alpha, you'd expect a positive correlation. Higher 2 should generally correspond to higher log mobitar.
And they choose Spearman rank correlation, or whole, as the specific test statistic. Why Spearman, not something like Pearson? For experts dealing with potentially complex neural net outputs, what's the advantage?
That's a really good point and a smart statistical choice. Spearman measures the strength and direction of a monotonic relationship between the ranks of two variables. Pearson measures the strength of a linear relationship between the raw values. With LLMs, the relationship between training step theory and the resulting log likelihood, log mubite, is unlikely to be perfectly linear. Think about SGD dynamics, learning rate schedules. It's complex. But you might plausibly expect it to be broadly monotonic. Later examples generally have higher likelihoods. Spearman focuses only on whether the ranks of theory tend to go up when the ranks of mubite go up. It's robust to outliers in the log likelihood values and doesn't assume linearity, which makes it much more suitable for this kind of potentially noisy nonlinear signal.
And using Spearman has a huge practical benefit here too, right, regarding the computation?
Absolutely massive. For a reasonably large number of samples, the null distribution of the Spearman correlation coefficient dollar under exchangeability, which holds if Stephen dollars is true, is well approximated by a student's t-distribution with ND2 degrees of freedom. This means Alice can calculate ND from her queried data, convert it directly to a t-statistic, and then get a p-value from the known t-distribution. No need for algorithm 1's expensive permutation simulation. They state it allows for extremely low exact p-values without being computationally bottlenecked. That's the key efficiency gain. Okay, but using raw log likelihoods, isn't there a risk that some texts are just inherently easier to predict? Like very common phrases or highly structured texts might always get high likelihoods, regardless of when they appeared in training. Wouldn't that noise drown out the subtle training order signal?
Yes, that's precisely the problem. This inherent variability in text predictability acts as a major confounder, reducing the power of the simple to-query test. It adds noise that makes it harder to see the correlation with $, which leads them to the refinement, the reference model. This feels like where the methodology gets really clever in terms of controlling for that background noise. Test statistic 2, file query.
Exactly. This is a critical improvement. The idea is to introduce an independent reference model, let's call it a number dealer. Ideally, the model should be a model of similar capability to Bob's model, a mu-beta, maybe from the same family, like another Pythia model, but trained on completely different data, or at least a very different ordering of the data, making it statistically independent of Alice's specific run alpha. Now, instead of correlating log vu-beta with t, Alice correlates the log likelihood ratio with t. Specifically, she uses the quantity log mu-d, which is the same as log mu-beta.
Okay. Walk me through why that ratio helps so much. How does it isolate the palimpsestic signal?
Think about it this way. If a particular text's dollar is just inherently very predictable, like the quick brown fox, both Bob's model mu-beta and the reference model OLMo dollar will likely assign it a high log likelihood, assuming they're roughly comparable models. When you take the difference, or the log ratio, that shared component due to inherent predictability cancels out, or at least is greatly reduced. What you're left with is the part of the log likelihood from Bob's model that cannot be explained by just general text modeling capability captured by $1. The hypothesis is that this residual difference is dominated by the specific memory imprint left by Alice's unique training sequence, alpha. So this difference, log mu-beta, should correlate much more cleanly with the training order dollar if mu-beta is indeed derived from alpha. It boosts the signal-to-noise ratio significantly.
So finding a good reference model in $0 is key. It needs to be similar enough in capability to capture the general predictability, but different enough in training history to not share the specific order signature. And they found models from the same family worked well.
Yes. Their experiments show that using a reference model from the same family, for example, a different Pythia checkpoint for testing a Pythia derivative, but trained on different data or a known different shuffle, generally yielded the best results, the lowest p-values for a given number of queries. It validates this normalization idea quite strongly.
What about practical constraints? What if Bob's API is really locked down and doesn't even give log likelihoods, maybe just the predicted next token? Is the method still usable?
They thought about that too. Alice isn't completely stuck. If she can only get token predictions, she can still estimate the token probabilities, and thus the log likelihood of a sequence. How? By repeatedly querying the model. For a given prefix, she can query many times to see the distribution of predicted next tokens. From that distribution, she can estimate the probability of the actual next token, $6. It's essentially Monte Carlo estimation of the token probabilities.
That sounds like it could require a lot of queries, though.
You might think so, but Appendix 8.6 has some pretty encouraging findings. They show that you can get surprisingly reliable estimates, maintaining high correlation with the true log likelihoods, even with a very small number of samples per token position. They tested any Tina, $4 and $16 samples per token, and found the correlation coefficients remained high.
Only 16 samples. That's practical.
Yeah, it suggests the query setting is viable even against APIs that only provide completions, not explicit probabilities, without incurring astronomical query costs for probability estimation.
Okay, let's get into the experiments for this query setting. The scale seems quite impressive. Multiple data families, Pythia, OLMo, tiny stories.
Right, 5 main pre-training transcript families. Pythia using the Pile, both deduped and non-deduped versions. Several OLMo versions using DOLMA v1.5, v1.7, and the OLMo mix, plus tiny stories mainly for ablation studies. And then the artifacts, beta-dellers, were over 40 different derivative models. They varied the size from 1 billion up to 12 billion parameters. And crucially, they covered a wide range of the common post-training techniques people actually use. SFT, DPO, PPO for alignment, even things like model souping. So a pretty comprehensive testbed.
First off, the baseline, testing a model against its own transcript. Does the palimpsestic effect actually show up consistently?
Yes, it does. Figures 2a, 2b, 2c show this clearly. When you test a model against the transcript it was trained on, you see a positive Spearman correlation enrolled. Now, importantly, the magnitude of randomness is usually small. We're talking values often between 0.001 and 0.1.
So the effect size for any single example's memory trace is tiny compared to the model's overall knowledge.
Exactly. But because Alice can query potentially millions of examples from her transcript, this tiny effect becomes statistically overwhelming. The p-values plummet as the number of queries increases, reaching extremely low levels, confirming the signal is real and detectable.
And how much did using the reference model help in practice?
It made a huge difference in efficiency. The results show that using the reference model approach reduced the number of queries needed to reach the same extremely low p-values by about an order of magnitude compared to using the raw log likelihoods with whoquery.
An order of magnitude. So, say, needing 1 million queries instead of 10 million to get the same level of confidence. That's a major practical saving.
Absolutely. It confirms that dealing with the inherent predictability noise via the reference model isn't just theoretically nice, it's practically essential for making these audits efficient.
Now, you mentioned Pythia earlier. Let's revisit that case study. It wasn't just confirming provenance, it was like forensic data auditing.
Yeah, this was a really striking result. They took the model called Pythia 2.8b deduped, which, as the name suggests, was documented as being trained on a deduplicated version of the Pile dataset. They tested it using Vedia query against both the deduped Pile transcript and the original non-deduped Pile transcript, using appropriate reference models for each. The result, against the non-deduped transcript, they got an incredibly significant p-value, $1, 2 times, $1060, which is vanishingly small. But against the deduped transcript it was supposed to be trained on, the p-value was not statistically significant.
Wow. So the test basically said, nope, despite the name and documentation, this model clearly remembers the training order of the original non-deduped data.
Precisely. It provides strong statistical evidence of data mislabeling or a documentation error. It really highlights the potential of this method, not just for detecting copying, but for verifying the integrity of the model supply chain itself. The training order signature is sensitive enough to distinguish between these versions of the dataset.
Okay, that's impressive. But the big question for enforcement is robustness. If Bob takes Alice's model and heavily fine-tunes it using SFT or DPO or RLHF, does the signal survive? Can he just erase it?
Remarkably, the signal seems very persistent. Across their suite of over 40 derivative models, covering all those common post-training methods on Pythia and OLMo, the p-values remain extremely low. They report p-values generally at most $10, and often much, much lower, like $10, $13, or in some cases even astronomical values, like 10161.
So fine-tuning doesn't erase the original training order memory. That seems counterintuitive. Isn't fine-tuning supposed to adapt the model significantly?
It adapts the model, yes, but it seems it doesn't fundamentally rewrite the deepest layers of memory laid down during pre-training, especially the parts influenced by data order. It suggests that alignment techniques might operate more on the surface, or perhaps they even rely on that underlying structure. The palimpsestic trace remains detectable through quite significant modification.
Did they find any way for Bob to evade detection in the query setting?
They did find a few cases, but significantly, only with smaller models, around 1.4b parameters, and only when the fine-tuning process was so extreme that it severely damaged the model's quality. The models that did manage to evade detection, meaning their p-value stayed above the 10 to the 5 threshold, showed drastically higher pre-training loss values after the modification, like 4.5 to 5.6, compared to a base loss around 3.0.
Ah, so there's a cost to evasion. You can try to scrub the signature, but you might break the model in the process.
That's the strong implication. To erase the training order, memory sufficiently seems to require modifications that cause significant degradation in the model's core capabilities. For anyone wanting to deploy a high-quality derivative model, this kind of evasion seems economically irrational. You destroy the value you're trying to capture.
And this idea of layered memory, the palimpsest concept itself, they tested that directly with multi-epoch training experiments too.
Yes, using tiny stories, and also looking at continued pre-training checkpoints for larger models like Pythia. The results are fascinating, shown in Figure 6 and 7. Even if you take a model checkpoint and continue pre-training it for many more steps, they tested an extra 70,000 steps on Pythia 6.9b. Or if you train for multiple epochs, where the data is reshuffled between epochs. The final model still retains a statistically significant correlation with the data ordering of the previous epochs or the earlier training phase.
So the later training doesn't completely erase the signature of the earlier orderings.
No, it's like the paper says, the previous orders are inscribed into the model along with later ones. The PAFA value for the Pythia 6.9b model against its base runs ordering, even after 70,000 extra steps, was still incredibly small, $2.23 times 1066 or more.
That really drives home the palimpsest analogy. New writing goes on top, but the old layers underneath are still detectable. It's not just about the last order scene.
Exactly. It suggests a much more complex, layered memory structure in these models than simple catastrophic forgetting might imply, especially concerning the impact of sequential data presentation.
Okay, let's switch gears now to the much tougher scenario, the observational setting. Here, Alice has no query access. All she gets is some text6 beta that Bob generated. This seems way harder because she has so much less information to work with.
It is significantly harder. The information asymmetry is huge. Alice basically has to work backwards from the generated text, using only her own original training data alpha and her knowledge of the training process to try and detect that faint correlation signature.
How does she even start? They propose two main strategies, right? The first one involves partitioning her transcript. Algorithm 2, Davapart Optas.
Right. Davapart Obs is the partitioning approach. The idea here is Alice takes her massive ordered transcript alpha and breaks it down into, say, Keller contiguous chunks or partitions. So partition 1 has the first unlike examples, partition 2 has the next color, and so on. Then for each partition Keller, she trains a separate, relatively simple statistical model, USIA, using only the data from that specific partition. Simplicity is key here for computational reasons. They often use n-gram models.
Okay, so she has models, each expert in a different era of her training data. How does she use these to test Bob's text Palimpsestic?
The test statistic needs to check if Bob's text 6 beta dollar shows more affinity for the models in Mujo trained on later partitions, higher dollars. The underlying assumption is the same palimpsestic idea. If Bob's model derived from the full run, his generated text should reflect the slightly stronger influence of the later training data. So Alice needs some way to measure how well 6 beta matches each partition dollar. Let's call this measure T dollar. Then she calculates the correlation between this match score take dollar and the partition index T dollars. A positive correlation suggests dependence.
What did they actually use for that match score in the experiments?
For efficiency, they mainly focused on using high-order n-gram models, specifically 8 grams, $8. The match score is simply the count of exact 8-gram overlaps between Bob's text of beta dollars and the set of 8 grams found in partition dollars. They built an index of all 8 grams for each partition.
So more 8-gram hits from later partitions implies provenance. Seems plausible, but relies on finding enough specific n-grams.
Exactly. It shifts the heavy lifting from training neural nets to building and querying potentially massive n-gram indices.
Okay, what's the second approach? Shuffling the transcript. Face, algorithm 3. This sounds computationally intensive again.
Oh, it definitely is.
Yeah.
This approach tackles the problem differently. Instead of partitioning, it uses the full transcript, 6 bil, or a relevant suffix of it, but compares the likelihood of Bob's text under different shuffles of that transcript. Here's how it works. Alice first trains a model, clear, using her original data sex file in its correct observed training order. Then she creates independent random reshuffles of the same data. For each shuffled dollar, she trains another model, mu-dollar, from scratch or fine-tunes from a common base on that shuffled data.
Retraining models multiple times. Yeah, that's expensive.
Very, especially for large models. To make it somewhat feasible, they often restrict this retraining to just a fraction of the original data, like maybe only the last 1%, 2%, or 10% of the training steps from alpha, where the order effect is presumed to be strongest and the retraining cost is lower.
So she has a new dollar and 5 byters shuffled orders. How does she compare them using Bob's text into coded dollars?
She calculates the log likelihood of Bob's text under each of these models, the log mu and glob's beta for all j-logger dollars. The test statistic is essentially a standardized score, like a z-score. It measures how much higher the likelihood is under the original order model, Sevilla level dollars, compared to the average likelihood under the shuffled order model's moduo. A large positive score means the original order gave a distinct advantage in predicting Bob's text, suggesting Sevilla d-dollar likely came from a model trained with that specific order.
And how do they get p-values from the z-score? Still permutation testing.
Here, because retraining for thousands of permutations, like in algorithm 1, is completely impractical, they resort to an approximation. They essentially treat the distribution of these likelihood differences, or the resulting z-score, under the null hypothesis as being approximately normal. This allows them to convert the observed z-score directly into an approximate p-value using the standard normal CDF.
An approximation, does that weaken the guarantee?
It means you lose the exact type I error control from Theorem 1. However, they note that empirically, this normal approximation tends to yield a conservative p-value.
Conservative p-value. Remind me what that means in practice for Alice.
It means the calculated approximate p-value is likely to be slightly larger than the true but unknown p-value.
Yeah.
So the test is actually less likely to make a false positive claim than the nominal significance level epsilon would suggest. If Alice gets a significant result using this approximation, she can be quite confident, as the test is biased slightly against finding significance. It maintains reliability, albeit cautiously.
Okay, that makes sense. Now, they also added a refinement to this phi-shuff method to handle cases where Bob might have fine-tuned Alice's model. It involves fine-tuning Alice's test models, too.
Yes, this is a clever step to improve robustness. The idea is, before calculating the likelihoods of Bob's text beta under a model and the shuffled midget models, Alice first fine-tunes all of these models, a little bit on Bob's text beta itself.
Why would she do that? Doesn't that contaminate her test models?
It seems counterintuitive, but the goal is to level the playing field. If Bob created 6 beta after fine-tuning Alice's original model, 6 beta will carry the stylistic and topical fingerprints of that fine-tuning. By briefly fine-tuning all her test models on 6 beta, Alice makes them all equally aware of and adapted to Bob's specific fine-tuning style. This helps to factor out the likelihood differences that are merely due to Bob's superficial modifications. What should remain, and what the test then focuses on, are the deeper likelihood differences stemming purely from the original pre-training order, present in only $40 but averaged out in the shuffled mu. It isolates the core palimpsestic signal from the noise of Bob's fine-tuning.
All right, let's see how these two observational methods actually performed. They seem to have very different profiles. Starting with the partitioning approach, Diyi-Lundbart, using null-and-Graham matching. How much data did it need?
The results here really underscore its main limitation. It's incredibly data-hungry. Table 1 makes it pretty clear. Even in the ideal scenario where Bob is just using Alice's model directly without any modification, Alice needs a lot of his generated text by dollars. We're talking hundreds of thousands of tokens, typically ranging from 640,000 up to maybe 1.28 million tokens, just to get p-values consistently down into the minimally convincing range of $10 or $10.
Wow, over 1 million tokens. So forget about using this to check if a single suspicious tweet or short forum post came from a specific model. That's just impossible.
Absolutely impossible. The authors explicitly state it's infeasible for short snippets. They see it as more suitable for larger-scale ecosystem-level analyses, like maybe trying to estimate what fraction of text on a whole platform might originate from a certain family of models, where you can aggregate huge amounts of text.
Does it hold up if Bob fine-tunes the model?
It shows some robustness. It could still detect provenance even after about 30,000 steps of fine-tuning, provided Alice had enough tokens, again, likely in the millions, but its sensitivity drops off, especially under certain generation conditions.
Like low-temperature sampling. Why would generating less diverse, more predictable text hurt an enneagram matching test?
Low-temperature sampling makes the model stick to very high probability sequences, often repeating common phrases or structures. This lack of diversity in the output 6 of beta dollar is bad for the enneagram test because the test relies on finding somewhat distinctive enneagrams that are more prevalent in later training partitions compared to earlier ones. If Bob's text only contains generic, high-frequency enneagrams that were common throughout Alice's entire training run, the differences between the partitions get washed out. The test loses its ability to discriminate based on the subtle ordering signal encoded in rarer enneagrams. You need diversity in the generated text for the partition differences to become apparent.
Okay, that makes sense. So, Talishubit's specialized. Needs tons of data, not for short texts, sensitive to low diversity generation. Now let's contrast that with the shuffling approach, Talishubit. This was the one that seemed token efficient but computationally heavy.
Exactly, and the results for Pythia OBS are, frankly, much more promising for scenarios where you only have a small amount of text. Remember, this is the method where Alice retrains models on shuffled data suffixes. In the tiny stories experiments, where they retrained models using just the final 2% of the pre-training data, they were able to get statistically significant p-values, less than $10, using samples of Bob's text sexbed as small as 320 tokens.
Wait, 320 tokens compared to over 600,000 for the other method? That's a game changer for practical detection.
It really is. It brings observational provenance detection down to the scale of paragraphs or short documents, which is much more operationally relevant for many use cases.
And did that refinement trick fine-tuning the test models on Bob's text actually help with robustness?
Yes. Figure 3 shows it quite clearly. Fine-tuning the test models on Macanavita significantly improved the test's robustness against Bob's own fine-tuning of the original model. It allowed Alice to maintain low p-values even when Bob had modified the model considerably.
But it wasn't infinitely robust, right? There was a limit.
Correct. The robustness has limits. The paper suggests that once Bob fine-tunes Alice's model, using an amount of data equivalent to more than about 1% of the original pre-training REN size, the effectiveness of Pythia starts to decrease noticeably. At that point, Bob's modifications begin to substantially overwrite even the deeper palimpsestic signal, making it harder for Alice's test models, even after their own brief fine-tuning on Sabeta, to reliably distinguish the original order effect. You can try to fight this by retraining Alice's test models on a larger suffix of her original data, but that just ramps up the computational cost again. It's always a trade-off.
So the method works well against moderate fine-tuning, especially with the refinement, but extreme fine-tuning can still potentially erase the signal, or at least make it much harder and more expensive to detect.
That seems to be the case.
Did they manage to test fine-shuff OBS on larger real-world models beyond tiny stories? You mentioned OLMo earlier.
Yes, that was important for demonstrating scalability. They cleverly leveraged the existing public checkpoints released for the OLMo models. Some of these checkpoints were trained on effectively the same large data set, 50 billion tokens, but using different known random shuffles of the data blocks. This allowed them to simulate the huge shuff scenario without doing the full retraining themselves. They could use one OLMo checkpoint as the original order model, $1 and another checkpoint, trained on a different shuffle of the same data, as a shuffled order model by $. So K-Hone is essentially comparing just two models. Even with this minimal setup, K-Hone comparing just two shuffles, they were able to achieve median p-values below $10.3, using only 640 tokens of generated text from the 7 billion parameter OLMo models.
Okay, so even at the 7B scale, using just 640 tokens, the difference between two known shuffles of the same data was statistically detectable in the generated text. That's strong evidence the order signal persists in large models.
It really is. It confirms that Pythia isn't just a theoretical curiosity or limited to toy datasets. The underlying training order signal is measurably present and exploitable even in large commercially relevant foundation models, provided Alice can get access to models trained on different shuffles, either by training them herself or using existing checkpoints.
So the observational setting boils down to this. Pythia itemgrams is computationally cheaper to query once the index is built, but needs massive amounts of text and struggles with low diversity. Pythia retraining is incredibly token efficient, working with just hundreds of tokens and more robust to fine-tuning with refinement, but demands significant GPU resources from Alice for the initial model retraining. Is that a fair summary?
That captures the core trade-offs perfectly.
So stepping back, what are the big practical takeaways here for people working in this space, folks concerned with model governance and accountability?
I think the biggest takeaway is that these methods demonstrate quite convincingly that non-invasive, transparent, and effective provenance tracing for black box models is possible. It's not just wishful thinking. The key insight they validated is that the way LLMs retain memory of their training data order, this palimpsestic effect, is a real, persistent, and statistically measurable phenomenon. And crucially, it can be exploited for forensic purposes without needing access to the model's internals or altering the original training.
But we need to be realistic about the costs and hurdles too. Let's talk brass tacks. The query setting, using query, how expensive is that likely to be in a real audit?
They provide some cost estimates in Appendix D, which are interesting. Using current API pricing for a relatively efficient model, maybe something like OpenAI's GPT 4.1 Mini, they project that running an audit using, say, 8 million sequences, which translates to maybe 64 million token samples queried, might cost around $180.
$180. That actually sounds surprisingly affordable for a serious investigation requiring strong statistical proof.
Right. It suggests that for targeted audits where you have query access and need high confidence, the cost might be quite manageable for organizations, definitely within the realm of standard compliance or forensic budgets.
Okay, but the observational setting, especially the token-efficient Fesheff OBS method, that's where the cost picture changes dramatically, isn't it? It's not API calls, it's GPU time for retraining.
Exactly. The cost shifts entirely to computation on Alice's side. Remember the tiny stories experiment. Retraining took about 10 minutes per epoch per shuffle on a single A6000 GPU. Now scale that up. For a large, say, 7B parameter model, even if Alice only retrains on the last 1% of the original pre-training data, which could still be tens or hundreds of millions of tokens and needs maybe K10 or K2 shuffles to get good statistical power, you're likely talking hundreds, maybe thousands of GPU hours.
Okay, that's a completely different league of expense. We're talking serious investment in computation.
Absolutely. It means FIDGFOPS, despite its amazing token efficiency, is probably reserved for high-stakes forensic investigations, where getting proof from a very small text sample is paramount, and the cost of computation is justified. It's not something you'd likely run routinely for broad monitoring. For comparison, the Ngram method, FEFIT part, needs huge disk space for its index, like 1.4 TB for Pythia they mentioned, but is faster to query once built.
Beyond cost, what's the biggest practical roadblock? It seems like it comes back to data access for Alice.
Yes, the data disclosure challenge is probably the most significant non-technical barrier. To run any of these tests, Alice needs access to her original ordered training transcript alphamero, or at least a substantial representative ordered subset of it.
And model developers might be hesitant to share that full data set, right? Due to competitive reasons, copyright issues, privacy concerns.
Precisely. If developers won't disclose the necessary ordered data, then independent third parties can't easily verify provenance using these methods. Creates a bit of a stalemate.
Do the authors suggest any way around that?
They offer a pragmatic compromise. Instead of demanding the entire proprietary dataset, perhaps Alice, or a third-party auditor, could run the tests using only the ordered sequence of data points drawn from publicly available sources within the larger training mix. For instance, focusing on the exact order in which Wikipedia articles or specific Common Crawl segments appeared during training. If the provenance signal is strong enough to be detected, even just within that publicly verifiable ordered subset, it could still provide very compelling evidence of lineage without requiring the developer to expose their full proprietary data mix. It's a potential middle ground.
That makes sense.
Yeah.
Focus on a part of the palimpsest that everyone can agree on the original rating for. So, wrapping up the takeaways. These tests work. They exploit a fundamental memory property. Query is affordable for audits. Observational has a cost-data trade-off, and data access is key.
I think that covers the main points. The research really validates that this subtle training order memory is a tangible statistical handle for governance.
It's a powerful demonstration that you can turn what might seem like a minor training artifact into a robust tool for accountability in this complex LLM ecosystem. Hashtag tag tag outro. So, just to quickly recap the highlights for you. If you have query access, the reference model method is remarkably token efficient. Powerful and efficient API use. If you only have generated text, the shuffling method, for reshuffle obs, is remarkably token efficient, potentially needing only hundreds of tokens, but you need to be prepared for significant retraining computation on your side.
And that leaves us with maybe one final thought to chew on, something this research brings into sharp focus for you as experts in the field. If it's true that the exact fine-grained training order leaves such a statistically durable trace in these massive models, a trace that survives multiple training epochs on reshuffled data, survives significant fine-tuning, what does that really tell us about memory? And, maybe more importantly, about erasure in neural networks. Forget just provenance for a second. If these order-dependent memories are so deeply baked in, what are the implications for fundamental privacy risks tied to the training data itself? Can we ever truly forget or remove sensitive sequences if their place in the original training order leaves a permanent statistical ghost? And how should these findings maybe nudge us to think differently about designing future models, perhaps aiming for architectures or training regimes where such deep order-dependent retention is less pronounced, or at least better understood and controlled?
That's a heavy question. The persistence of memory, even just the memory of sequence, having such profound implications. We certainly hope this deep dive has given you a clear, thorough grasp of the source paper, its methods, findings, and these broader implications. Thanks for joining us.